Okay. In the previous class, we have discussed about traditional machining process like lathe machining, drilling, grinding, all the things we have discussed. Now we are going to enter into this thing that is non-traditional machining process. In non-traditional machining process, okay, fine. What is the difference between traditional and non-traditional machining process? Anyone? Anyone who can let me know the differences between traditional and non-traditional machining process? Of course, it is new. That's true. New doesn't mean that we have to use it. It has to have some improvement in comparison with the traditional manufacturing machining process. Am I right? So how come it is different and improved version of traditional? Okay, fine. Accuracy is there. And any other things that you know of? True. Material wastage will be there, but it might be less. That's true. And any other? Okay. So let's discuss. Let me give my understanding of differences between traditional and non-traditional machining process. One, in traditional manufacturing, we have seen that there is a contact between tool and workpiece, isn't it? We have seen that you have to have a physical contact. There has to be a physical contact between workpiece and tool, right? Be it milling, drilling, grinding, whatever machining process that you're trying to do, you have to machine by using a harder tool, and that tool will be in contact with the workpiece. But in the case of non-traditional machining process, it need not be true. It can have physical contact, or it cannot also. It's not necessary that it has to have physical contact. Without having physical contact also, you will be able to use this machining process to remove material from the workpiece. Another thing is your tool has to be harder. Yes, like laser cutting, you're right, Prakar, like laser cutting, there is no need of any contact. Another thing is that in the traditional manufacturing, you're using mechanical forces as your cutting force, right? But here, in this case, it's not only mechanical force or mechanical energy, it can be thermal energy, it can be electrical energy, it can be chemical energy, it can be this kind of energies, not the traditional mechanical. We are using different kind of energies that can be used to machine or remove the material from the workpiece. And also, as there is no physical contact between workpiece and tool, the criteria that the traditional manufacturing machining process is having, what is that? Your tool should be harder than the workpiece. And here, there is no requirement that your tool should be harder. Your tool can be as softer as possible than the workpiece. But yet, you can use the tool to machine the workpiece. Is it okay, guys? Fine. Now, let me go through these things. New materials having high strength and hardness, such as pneumonic alloys and alloys with alloying elements such as tungsten, molybdenum, aluminum, are difficult to machine by traditional methods. Why? Obviously, if you want to do machining with traditional manufacturing machining methods, your tool has to be stronger than these elements. And finding a tool which are stronger and harder than these elements is very difficult for us, and also it will be very costly. That's the reason why we have moved on to the non-traditional machining process. Another thing is that in conventional machining, the MRR reduces with an increase in work hardness. Obviously, as the material removal rate will be reducing as the workpiece is harder, right? Because the more harder it is, the more friction it is generated between the tool and workpiece, and the tool wear is very high in the case of uh, conventional machining. And also you can't give good feed and depth of cut because you are cutting very harder material. Because of lesser depth of cut and lesser feed, what happens, your MRR keeps on reducing, and that is not good. And in non-traditional manufacturing, no need. Even though you are having a very harder material, you can remove material as fast as possible. And complicated shapes can be manufactured easily in the non-traditional machining process. In traditional, like milling, lathe, there are fixed. For milling, you have to have, you wanted to create a flat surface, fine. For lathe, you're creating a cylindrical surface, fine. For drilling, you're drilling a hole, fine. For grinding, you're creating a good surface roughness, fine. But if there are some very complicated structures or complicated geometries or shapes, it's very difficult for us to machine by using traditional. But yet, we have this non-traditional machining where highly intricate shapes can be manufactured. And besides, obviously somebody was mentioning you can achieve a very good accuracy in the case of non-traditional or unconventional machining process. Right. Next, this is what I was talking about. Different forms of energies are directly applied to remove the material. What are those? Mechanical, chemical, electrical, thermal, heat, anything. You can apply any available energies, and you can convert that into we can convert that workpiece into a defined shape. No chips, of course, because there is no point of chips, because you are heating the material. If you are using thermal, you are heating the material. When you are heating material, there will be a chip. The material will be melted away, right? No lay pattern. Lay pattern in the sense, like if you're doing the turning, what happens? There are some feed marks that are left onto the turned piece, and you that kind of things will not be obtained, or will not. This pattern is not formed, and hence the surface roughness is very good in this case. No direct physical contact between the tool and workpiece. That is what I was talking about. Material need not to be harder than the workpiece. That is also I have told. Does not increase. Tool forces does not increase as the workpiece gets harder, right? Because here also what I'm talking, the workpiece can be as harder as possible, and tool can be as softer as possible. But because of different type of energies, you'll be able to remove the material. But the material removal rate does not decrease as the work is getting harder. That's what I told you. Okay, fine. So let's classify this non-traditional machining process into four, based on the energy that we are trying to use. What are the four energies? Thermal energy methods, electrochemical energy methods, chemical energy methods, mechanical energy methods. So these are the four categories. In that, we are going to discuss electric discharge machining, which is coming under thermal energy methods, electric discharge machining, laser beam machining, plasma arc machining, electron beam machining, ion beam machining. All these things will come under thermal energy methods, where you are using thermal energy as a primary source of energy, where you want to remove the material from the workpiece. Electrochemical energy methods, that are electrochemical machining, electrochemical grinding. In chemical energy methods, we are using chemical machining. CHM is chemical machining. Mechanical energy methods, under that we have ultrasonic machining, abrasive jet machining, water jet machining. Right? So these are all the different type of non-traditional machining process in which we are categorizing them with the respect of energies that we are trying to use. Fine. Let's go and discuss a little bit of electrochemical machining. Electrochemical, electricity, chemical, what you say, chemical energy. So electricity is there, so electrical energy. Chemical is there, chemical energy. So we are trying to use electricity and chemical, some chemical processes. What is happening here? Let's see the diagram here. In this diagram, if you see, there's a workpiece here, and there is a tool, and tool is having some kind of a different shape, and you want to try to have that kind of shape impinged onto this workpiece. Okay, so this is what you want to achieve at the end. The right hand side figure, this is what you want to achieve at the end. So now what I'm saying is that if you want to have this kind of thing. So the negative of the shape that you wanted to form on the workpiece will be onto the tool. Fine. Now you are dipping this workpiece and tool in some kind of a fluid, okay, and you are connecting the workpiece and tool with some circuit, some electrical circuit, and you have some, you know, this terminal here. Now what happens? This fluid that you're trying to submerge your tool and workpiece is known as electrolyte. This is what is electrolyte. And please do remember, the important point is that here workpiece and tool both have to be electrically conductive, because you're trying to connect them with the terminal and you want the electricity to pass through this workpiece and the tool. That's the reason why the main criteria for this kind of for this machining is your workpiece and tool have to be electrically conductive. Now what you'll do, once you're dipping this workpiece and tool into this electrolyte, and once you close the circuit with this terminal, what happens? Electricity starts to, flow. And as electricity is trying to flow, obviously there is a gap between workpiece and tool. In this gap, you can see this is electrolyte. This electrolyte is in between your tool and the workpiece. And workpiece is of some material, tool is of some material. Electrolyte, what is electrolyte? It's nothing but a salt solution, neutral salt solution. Salt, what is salt? NaCl, sodium chloride. And there is a sodium chloride in between. Sodium chloride plus water is the electrolyte. And as electricity is trying to pass between workpiece and tool, and there is a salt solution in between, there is some kind of a reaction that is happening in between workpiece and tool. That reaction is what is the chemical energy that is generated. Because of that chemical reactions, slowly some amount of material of workpiece will be removed, and as we keep on moving tool from left to right side in the direction of left to right, you see the workpiece is getting removed in this kind of a shape. So what exactly is happening in this thing? It's nothing but it is anodic dissolution at atomic level. In the sense, your material is dissolving at atomic level by having this anodic reaction. What is anode here? This is anode, this is cathode. Anodic dissolution. Anodic dissolution is in the sense workpiece is getting the material removal rate. Workpiece is being removed, or workpiece is being eaten away. So that is why it's called anodic. Workpiece positive, anodic dissolution. Workpiece is getting dissolved slowly with the help of this kind of setup. Okay. So at steady state, you can see this kind of a shape is being formed out of the workpiece. And here the important point that you have to note is nothing but this process needs good current, high current, because the current has to be flowing very high, then only these kind of chemical reactions can be ignited, and we should use low voltage. So please do remember, electrochemical machining is a high current and low voltage process. Okay, fine, let's move on. Now, during this process, what is happening? Let me show here. I don't want to show any. These are the reactions actually. You don't want to worry about these reactions. Don't worry about these reactions. But what I'm going to say is this diagram is very important. What is happening here? You see, obviously workpiece, generally what we machine, let's assume that, in this case, let us assume that workpiece is having iron in that Fe. And tool is having some, it's a cathode. Forget about which material it is. Workpiece is having some iron content in it. Okay, fine. Now, and what is floating? What is liquid? Liquid is nothing but NaCl, that is sodium chloride. After certain reactions, sodium chloride has been dissociated into Na plus atoms and Cl atoms. Okay, let me write it and explain to you. So this is sodium and this is chloride. Sodium chloride has been dissociated because the electricity is being passed. So electricity is being passed, current is being passed, high current. And water, sodium chloride plus water is your electrolyte, right? So water has been dissociated into H plus and OH minus. Okay, this is another reactions. And as anode, cathode is there, electricity is being passed. So this is anode, so positive ions will be developed at this point, positive, because this is positive terminal, right? So Fe plus atoms are coming out, and at negative OH, this OH minus atoms are coming out. Okay, why OH minus? Because H2O is divided into OH minus, so that's the reason why all the negative atoms are here, or maybe you can say some electrons are generated. Negative cathode, no negative. Now you see this Fe and Cl, this Fe and Cl are formed, and Fe and OH are formed. This FeCl is giving FeCl2, and OH and Fe are giving FeOH2. In the sense, iron is dissolved into Cl chloride. Iron is getting reacted with hydroxide atoms. Now what I will say is that it means that slowly, atomically, these are atoms, right? Atomically, this Fe is coming out from the workpiece and getting chemically reacted with Cl and OH, and then this FeCl2 and FeOH2 are formed, and this FeCl2 and FeOH2 are called precipitates, or they are called some kind of a sludge. They are having good amount of weight density, so they'll fall down, and that material is your material. So what is this? FeCl2 and FeOH2 are material removed from the workpiece. I mean, of course, Fe is removed, but Fe is trying to form its reaction with chlorine, and Fe is trying to form the reaction with OH2. So here, let's not go into depth. This is what is the main understanding here. In the sense, what is happening here? Fe is getting dissolved into the electrolyte with some chemical reactions. It means workpiece is getting removed at atomic level. In the sense, what is removed? Removed in the sense, material is getting removed slowly. So that's the reason why this is called electrochemical machining. Am I okay? Am I clear with this concept, guys? Are you getting this concept? Okay, fine. So this Fe and so this is, you can see here, this FeCl2 and OH2. How is required state to be achieved? Because you are putting this tool, you are making your tool in this kind of a shape. So that that negative will be formed here. That is how your required shape is achieved. Is it okay, Ravi? Yeah. So if I want to make some kind of, what is this shape? Anyone? What is this shape? What is this? What is this? Anyone? What is the shape? Have you seen this kind of a shape anytime? Aerofoil. Yes. So if you go to HAL, these are aerofoil blades, turbine blades, or maybe some kind of a blades there. If this aerofoil shape you want to manufacture, what you do, you have negative aerofoil structure onto the tool, and this kind of structure is formed onto the workpiece here. Understood? So this structure is given to the tool itself. The tool will try to get some chemical reaction. This workpiece is converted into like this. Is it okay? Yes. So that kind of things are manufactured in HR also. You can see electrochemical machining is used to manufacture this kind of blades, okay? Aerofoil shapes, and with good accuracy and precision. Fine. Now, so this is the equipment. You see, this is your tool. Okay. So let's not give more info about these things, but I'll tell you some basic info. Okay, there are so many things here. Don't worry much about that. Some important points or some important labels I'll be able to explain here. So this is tool, and this tool is like this, and this tool is given some coating so that tool is not getting material removed, because obviously chemical reaction is happening in between tool and workpiece. Even though workpiece is given anode, the current electrons passes from tool to a workpiece, that's okay, but tool also will be having have some kind of material removal. To avoid that, some coating is done. Okay, and also you see this tool is having certain shape, and that kind of indentation is formed onto the workpiece, and this is complete setup is under electrolyte. And now as you are doing this kind of in the previous slide, we have seen some kind of reactions are happening, and this precipitate is formed, and that precipitate is mixed into the electrolyte. You want fresh electrolyte every time. You don't want your electrolyte to be polluted, right? So what you do, you take that electrolyte, you just take into some kind of a this thing using some centrifuge. You make the electrolyte into this thing, you flush it, and then it is going into some kind of a processor here, centrifuge. And in this centrifuge, what happens? High density particles will be away. That is your metal removed, and low density liquid will be at center. So you remove that, and then the sludge will be taken away, and fresh electrolyte, which filtered electrolyte is taken into like this, and there are some secondary filters here. Then it is sent into this kind of a tank here, and from this tank, they use pump to suck the fresh electrolyte, and then it will go into some kind of flows. All this control is there, and then it will enter into the same work zone like this. It will enter into this. In between there is a gap here. Through that gap, this why they are kept in between? Because some material which is there here, they have to flush it out. So that is called flushing mechanism. So they use some pressure like this. With that pressure, then this material will be removed and it will come from both the sides. So this is what is the equipment schematic diagram of your electrochemical machining unit. Right. Next, in electrochemical machining, I want to know what is the material or how much is the material they are trying to remove. So in electrochemical machining, mass of material removed is directly proportional to charge of the electricity. And what is charge? Charge is nothing but current into time. So mass is directly proportional to current into time. And if you remove this proportionality constant, you get mass is equal to Z into IT. So what is this Z? A proportionality constant, and that is having some name, and that is known as electrochemical equivalent. Electrochemical equivalent. An electrochemical equivalent is having some formula. That formula is chemical equivalent by Faraday's constant. Please do remember this Z is electrochemical equivalent, and E is this E is chemical equivalent. Okay, please remember E is chemical equivalent, and F is Faraday's constant. And what is chemical equivalent? Chemical equivalent is nothing but atomic weight by valency. What is valency, sir? Anyone? What is valency? Valency of, hello? If we have some material, what is the valency of that material, whatever it is? Anyone? Not free, the outermost free electrons, if you can say, that are ready to pair, right? The outermost orbit, some electrons are free, and those are called, yes, fine, you know that. So for a given material, you have some atomic weight and valency. So E is given by A by V. A by V is E. So if you substitute this equation here, that will be A by V into F. Okay, fine. Now I want to calculate material removal rate, not mass. So obviously, what is material removal rate? Volume of material removed by time. So I have mass here. So I want to convert that mass into volume. How do you convert? Divide this volume of material by mass of the material by density. Then what will you get? You will get volume. So that is how I am substituting volume of the material by mass by density. So if I substitute mass by density, and this time is T here. So already I know that mass is what? ZIT. I substitute ZIT divided by rho T. TT gets cancelled. So then ZI by rho, right? So what is ZI? ZI is nothing but E by F. So if you substitute E by F, then E by F, I by rho. These two are there. So from here, and then if I substitute E is equal to A by V, then A into I by rho VF, then this is your minimum. So you have to remember this formula. If you want to remember in the terms of chemical equivalent, you remember as EI by rho F, where E is equal to A by F. A by V, sorry. V is valency, A is atomic weight. Or else you directly remove this, remember this formula. How? AI by rho VF. AI by rho VF. Please write this formula. AI by rho VF. MRR in electrochemical machining is A into, that is atomic weight of material, into current passed divided by density of the material into valency of the material into Faraday's constant. Faraday's constant is constant, that is 96500. Okay, so this is what is the formula for your material removal rate in the electrochemical machine. AI by rho Vf. Okay, next. And next, this is very important, and also there is one more thing called specific material removal rate, that is given by material removal rate by the current fast. That is what is specific material removal rate S, and current density. So these are all some immediate intermediate formulas. We don't have any much derivations here, because if you want to derive completely what is happening, we have to draw some circuit diagrams and all. That is not required here. Current density is equal to what? Generally, if you generally in terms of electricity, current density is nothing but current divided by surface area, and I is what? Delta V, that is change in voltage divided by the resistance. What is resistance? Resistivity into L by A, length that is acting, the length of that resistivity divided by the area of cross section, where L is the length of workpiece, length between the workpiece and tool. That is how the length gap. So what is the length between workpiece and tool? The small gap here is the length between the workpiece and the tool. That is what is the gap between the workpiece and tool. That is what is there. That is where the electricity is being generated. That is where the resistance is offered, because your tool is here, your workpiece is here. You want to have the tool and workpiece to have conducted. So, but still there is some kind of a liquid that is opposing this electricity, and that is what is where the resistance is being generated. Because of the resistance only, and because of the voltage difference, this current is being passed. Delta V by R is equal to current, high current you are trying to put. Okay. So finally, you can remember this formula. Forget about this thing. That is your, what is this? Specific electrode. Sorry, current density J is this. Current density J is K into conductivity into delta V by L. Change in voltage by length between the workpiece and tool. And electrode feed rate. So finally, why I have done all these things is because because of this electrode feed rate. What is electrode feed rate? Electrode feed rate is nothing but, because once you okay, let me draw some series of diagrams, you'll understand that. So initially the workpiece is like this, tool is like this, then after some time the workpiece will be touching, it will be like this. Then what will happen? The workpiece will be removed something like this, and after some time of course, sorry, and after some time what happens? You will think this like this. Obviously your tool has to come down to adjust this gap, right? Your tool is coming down only, then as the tool is coming down, the workpieces will be getting removed, and the gap between tool and the workpiece is maintained constant. That is what is the electrode, the gap between workpiece and tool is constant, and you are maintaining that gap. Even though material is removed, material will be removed somewhere, and you have to feed this tool in such a way that you are maintaining some certain constant distance. So you have to give a feed to the tool, and that is what is your electrode feed rate. That is S into J. What is S? Specific material removal rate. S into J is your the specific, the current density. Okay, current density S into J will give you electrode feed rate. How do you provide this feed to the tool so that the gap is maintained constant? Fine. So these are some, okay. So that's the end of electrochemical machining. Let's go to electric discharge machining. What is electric discharge machining? Electric. So you are using some kind of electricity. Discharge. We have to see what is this, what is discharging. We have to see. Of course, machining is there. So now what we'll do is that let's discuss the diagram here, and then we'll go back and discuss why this name is given as electric discharge machining. And this comes under electrothermal non-traditional manufacturing process. Here what is happening, in the same like previous case, tool is there, workpiece is there, and both are submerged in some kind of a fluid. There it is electrolyte, which is a sodium chloride based solution, right? Sodium chloride plus water. Here it is submerged in a fluid called dielectric. The fluid name is dielectric. And that dielectric fluid, sir, what is that? One of the examples for dielectric is kerosene. Some kind of a kerosene, different grade of kerosene, not in general kerosene that you buy in the market. Some petroleum based product, but it is kerosene. Okay, you can directly fill this tool and submerge this tool and workpiece in kerosene, or you can call it as a direct fluid. There it is electrolyte, where in ECM. ECM is nothing but electrochemical machining. EDM is electric discharge machining. Now, if you are submerging this tool and workpiece in electrolyte, in dielectric. Now you are connecting this tool and workpiece to some kind of terminal, and you are closing the terminal, and the current is passed. And please remember, again in this case also, your tool and workpiece have to be electrically conductive. In electrochemical machining and in electric discharge machining, in both the cases, your tool and workpiece have to be electrically conductive. Okay. Now what happens? As this tool is having given negative terminal and workpiece is given positive terminal, the electrons will try to pass from, like this, from negative to positive. But the current will not. There's a gap here. Obviously, there's a gap here, and this gap will be acting as a resistor, because your electricity will not pass between tool and workpiece. Why? Because there is some gap. If they are both are attached, okay, fine. But there is a gap, and that dielectric fluid which is in between the tool and workpiece is not allowing the current to pass. Then what happens? There is some mechanism. I'll tell you what is happening exactly. There is some mechanism. After giving high voltage, provide good potential difference, in the sense high voltage, at certain point of time, this electrons will discharge, in the sense there is some kind of a column that is generated momentarily, very short amount of time. There is some series of sparks that are generated, in the sense there is small kind of a time gap where the dielectric constant, that the dielectric fluid will allow the electricity to pass from tool to workpiece. Right? The electrons will pass from tool to workpiece. Electricity is passed from tool to workpiece very momentarily, but when it is trying to pass, when this current is being passed very momentarily, in fraction of seconds, okay, some kind of spark is generated, and that spark is generated with huge temperature at the order of 10,000 degrees centigrade. 10,000 degrees centigrade. You are hearing right? 10,000 degrees centigrade. So for that momentarily, that spark is generating so much amount of temperature. That temperature will heat the workpiece at that spot momentarily, very small amount of time. Okay, heat the workpiece and tool as well, obviously, but job will have more temperature. And when that heat is happening, there is some kind of a melting of workpiece is happening. Too much amount of heat is generated. No, melting of workpiece is happening. As the melting of workpiece is happening and stopping, and dielectric fluid also is there, evaporation of workpiece is happening. Melting, full liquid, evaporating. So the mechanism through which the material removal rate is happening in the electric discharge machining is melting and vaporization. Is it clear, guys? Is it clear? Hello? Yes. Good. Fine. And do remember, in the previous case, I told you ECM was high current, low voltage, but electric discharge machining is low current and high voltage. Please remember, both are reverse in nature. There we have to have good current. Here we have to have good voltage difference. Okay. And this is what is happening. So I told you, right? Like arc wants to pass. There is a kerosene, and the arc jumps with the least resistance. And then when some kind of energy is concentrated, and suddenly spark is generated. When spark is generated, 10,000 degrees centigrade for very small time is generated. This will melt more, obviously, because terminal here that is negative, this is positive. Okay, this is tool. Okay, the upper one is tool, the bottom one is workpiece, and there is some kind of this fluid, whatever this melts is exploded, and then particles are floating here and there, and it will be mixed into the dielectric fluid. That is how these are all material removed, material that is being removed from here. Okay, workpiece. So it's a very complicated mechanism, but yet it's very important to understand that melting and vaporization is the mechanism through which material is being removed from the workpiece by using electric discharge machining, EDM. Okay, what is discharge? Discharge of column of electrons, spark. Okay, fine. So this is modeling. This is not much important for gate. Also, not much is important. But let's understand here what is happening. Here you are not trying to pass this current in a serial way, sense like direct current. We are giving it in the terms of pulsed mode. See, this is a pulse on, T off, T off. Okay, so this is tool, this is spark, and there's some kind of a crater that is formed. I told you, very small amount of time, huge temperature is generated, and some kind of hemispherical crater is formed. This is what is called hemispherical crater. What is the volume of hemispherical crater? Volume of hemispherical crater is 2 by 3 pi r cube, right? So, and also here, energy of the spark that is generated is directly proportional to the T on, obviously. Energy is directly proportional to T, energy is directly proportional to voltage, energy is directly proportional to current. So this is what is energy, right? And the work energy of spark is this, but not total energy of spark is utilized on removing workpiece. Some amount is removed into tool also, but yet whatever energy that is created in this spark is directly proportional or is utilized onto the workpiece. Hence, the energy that has been used on the workpiece is directly proportional to the energy of the spark. So this is how the derivation is keeping on going. But this is the formula for your material removal rate in the case of electric discharge machining. It's not a very important formula, but yet please do try to understand what is the relation. So here, MRR is directly proportional to voltage, MR is directly proportional to current. Here, please remember, voltage is obviously dominating the current. High voltage, low current process, divided by 1 plus T off is your the off time of your pulse, and T on will be your on time of your pulse. So these are your electric discharge machining formula for MRR. And next is there is servo mechanism. We have to import it. I told you, right, in the previous case we have calculated the electrode feed rate. What was electrode feed rate? Electrode feed rate was S into J, right? In the previous case, in the electrochemical process, we have seen that. In ECM, what did we see? In ECM, we have seen that the electrode feed rate, the feed rate of electrode is equal to current, the specific material removal rate into current density J, right? Why you are giving that feed rate? So that as your tool is coming down, the workpiece also will be removed. Obviously, as the workpiece material is removed, your tool has to come down. The tool has to come down with some speed. What is the speed? That speed is your electrode feed rate. Okay, but here also you have to maintain a constant gap between your workpiece and tool. Okay, that is what has been exaggerated here. If you want to see here, see, this is what is, so this small gap has been exaggerated with this. So this is what is called your spark gap, the gap between the workpiece and tool. So this is workpiece, and this is tool, and this is workpiece. Okay, so how do you maintain constant gap? Obviously, you have to have some kind of a mechanism. So there is some kind of sensor, which will automatically understand that, oh, this is the gap that is between workpiece and tool. Okay, tool, you come down so that workpiece and tool will be having same gap. So for tool, you use some kind of a feed which will maintain that constant gap between workpiece and tool, and that maintenance can be done by using this servo mechanism. This servo mechanism is used to maintain the constant gap between the tool and the workpiece. Okay. Now again, same thing like previous schematic. You see, there is a flush, and some material which is there. This will pollute. Already material removal which is there is polluting this dielectric constant. Dielectric fluid, that is what is kerosene, and that dielectric fluid is taken here. Then it will go into a pump. Then there is a filter, and there is something like flushing. What is this flushing? Because there are some material removed material that is getting in between the spark gap, that has to be flushed away. So you are flushing it with some pressure here, and some filter is going into this thing, and again it is flushing here also. So this is how the material which is removed in between tool and workpiece can be flushed away by using this flushing mechanism. Okay, fine. And let's not get into this. So this is a very big circuit in the discharge electric discharge machining. This circuit is there, and through this charging time, discharge time, so this is why it is called discharge. There's a discharge time here. Okay, charging, discharge, and charging T on, discharge T off. There's so many things. Okay, so because of this resistance, capacitance, relaxation circuit only, this pulses are generated. Okay, and during that pulses, all these things are happening. That is, V is equal to V naught. All these things, you don't worry. Anyways, if you want, you can take this snapshot and remember these formulas. I'll give you some 10 to 15 seconds. You can take the snapshot, and or else if you want to write them clearly, then you can view the video and then take the snapshots, or maybe you can write the formulas in your short notes. So these are the formulas for voltage across the gap at any time, and time constant, all these things. Again, I'm just putting the slides for the sake of video. Just you can use them. Pause your video when you are seeing the recordings, and then you can write them and use it in the examinations. Okay, so let's not, these are all formulas. There is no need of any explanation here. I am not deriving them because you have to understand everything about the circuits and all. Let's not do that. Okay, so formula page 1, formula page 2, and formula page 3. So pause the video and then you can write the formulas in your short notes. Okay. Next is electric discharge machining, having another kind of utilization in the terms of wire idiom. What is wire idiom? In this case, what did we see? We had some tool, and that tool is having some kind of a shape which is opposite, or which is a mirror image of the workpiece, or mirror image that you want to form onto the workpiece, right? Or the shape of workpiece that you want to form will have a mirror image on the tool, so that kind of indentation is formed. That kind of shape is drawn here. See, this kind of a shape that you want to form. So this kind of shape is formed. But let's say you want to cut a big thicker plate. This is a plate, and you want to cut into two halves. Let's say, and you can cut that very nicely with the help of wire idiom. Same things are there. The same mechanism. There, they are dipping the workpiece and tool in the in dielectric fluid, right? Here, instead of tool, we are using wire. So wire is the tool here, and there is a spool here. That wire is wounded to some spool. It is unwounded, and then it is coming like this. It is wounded here. Continuously, this wire will be unwounded here in the top one, wounded here in the bottom one, and it will wound like this. As the wire is being passed, you continuously supply this deionized water. So here, dielectric fluid is deionized water. Please to remember, in a conventional electric discharge machining, we are using kerosene as dielectric fluid, but in wire idiom process, we are using deionized water. So same mechanism will happen. Again, same mechanism here. Some high voltage, then some threshold is reached. Again, discharge is happening. During discharge, some spark is generated. High amount of temperature is generated within small amount of time. Some material will be melted, then vaporized. Everything is same mechanism, but the only change that is happening here is tool is wire, and it is continuously passing between into this space, and the cutting this workpiece and the wire are kind of submerged in the deionized water, because you are continuously passing the deionized water onto the gap between tool and the workpiece. What is tool here? Wire and the workpiece. Okay, so wire idiom is a special form of idiom wherein the electrode is continuously moving through the conductive wire. Thin wire of brass or tungsten or copper is used as electrode. So this is wire which is having a material of brass or tungsten or copper. And the electrode wire is typically made of 0.3, very thin material. So the cut is very fine here, 0.05 to 0.25 mm diameter, very small wire. And deionized water is used for dielectric, and this process is much faster than normal idiom, because see, this is how, this is a gap. You see, the gap is generated here, and in this gap only the sparks are generated. It will keep on moving like this. Fine. So next is ultrasonic machining. So in this previous to ECM and EDM, I clearly mentioned that the material, that is workpiece, and the tool material, that is tool and workpiece, have to be electrically conductive. So what if your this workpiece is not conductive? So it's not necessary that every time you are trying to machine some electrically conductive materials, right? Electrically non-conductive materials also you should be able to remove them. How can you remove? How can you remove them? I want to have good precision and all these things. So then there comes here ultrasonic machining. What is ultrasonic? Here we are using some vibrations. So mechanical vibrations are created. Because of that mechanical vibrations, the material removal rate is happening. So what is happening? Let's see. So workpiece is this, and this is tool. So in between workpiece and tool, in the first case in ECM we had electrolyte. In the second case EDM we had dielectric fluid. In this case we have some abrasive particles. It's called abrasive slurry. Slurry in the sense some abrasive particles mixed with water. What are these abrasive particles? Like in grinding wheel, we have some stronger, harder abrasives, small abrasive particles. In the same way, here also we have some abrasive particles which are harder than the workpiece. And these abrasive particles are mixed into the water. And that abrasive slurry is allowed in between the tool and the workpiece. Fine, I allowed, sir. Now what I have to do? Okay, now what I have to do is that you give this tool some kind of a vibration with the help of some transducer. I'll show you the setup. I'll show you the schematic of ultrasonic, then you understand how the vibrations are generated. But yet now, as of now, you understand somehow we have given some vibration like this, some vibration like this. As this vibration is given for the tool in the ultrasonic range, now what happens? See, it's the vibration frequency is 19 to 25 kilohertz. And amplitude is very small, micro amplitude in the wave. This is what is amplitude, right? Very small amplitude, and you can't even see whether tool is vibrating or not. But yet at ultrasonic level, it is vibrating. As this tool is vibrating like this, now what happens? Some kind of vibrations. Obviously, when somebody is vibrating, some energy is given. So the force that is there, at the velocity, that is when the vibration is so it is hitting this one of the particles, and this particle is attaining, so let's say assume this particle is there. This particle is attaining some momentum, mass into velocity. Some mass is there, some velocity generated, momentum, mass into velocity, and that momentum is going and hitting the workpiece, right? So this particle is attaining some momentum and hitting the workpiece with high velocity. Because of high velocity, the workpiece is getting some kind of an indentation here. It is removing the material soft, because obviously these abrasives are harder than the workpiece. And remember, this tool need not be harder. It can be anything. It needs to be having, it needs to have some kind of vibrations. That is what is important. Okay. So once this material, this abrasive particle is hitting the workpiece material is removed. How it is removed? First it will hit. Once it is hitting, some crack initiation is happening. After some time, the crack will propagate, and then there is a brittle fracture. Obviously, this kind of machining, generally ultrasonic machining is used for machining some ceramics, some brittle objects. Okay, so because of that, crack and propagations are very easily done, and brittle fracture is done. As the fracture is done, what is happening? The material will be removed from the workpiece in the small pieces. Okay, that is how the material removal is achieved in ultrasonic machining. Vibration of tool leads to momentum of abrasive particles in between. Due to the momentum, crack initiation onto the workpiece, then crack propagation, then brittle fracture. That's how material removal rate is happening. Is it clear, guys, how ultrasonic machining is working? How ultrasonic machining is used to remove the material? Yes. Good. Next. So this is what I've told already clearly. And this is how this thing is there, and all these things you can read. Yeah. Okay. So this is your simple process effects, and we have to discuss this. Very important. What is this amplitude? So sometimes questions can be asked like this. So what if amplitude is increasing? What happens to the MRR? Obviously, good amplitude in the sense huge amount of vibration. You can see that vibration, big vibrations are happening like this, right? So obviously, as amplitude is increasing, your material removal rate will increase. For a fixed feed rate, this is what is happening. If your feed rate is increasing, obviously this kind of graphs are obtained. In any case, you take any case of feed, you see if amplitude of vibration is increasing, material removal rate will be increasing. That is for sure. Next, if at all you see the frequency of vibration is increasing. Frequency in the sense how frequently you are doing that vibration, how fast you are doing this. How long you are doing is amplitude, and how fast you are doing is frequency. If your frequency also is increasing, obviously material removal rate also will be keeping on increasing. Okay. And what about the material removal rate if diameter of abrasive particles are increasing? If diameter of abrasive particles increasing, I mean, since the particles are small, then the particles of abrasives are increasing in between. Then what is happening? Diameter of abrasive particles are increasing. Then what happens? It'll keep on increasing because diameters are increasing in the sense mass is increasing. Mass increasing in the sense the momentum is increasing. Momentum increasing, more hard it will hit, more indentation is formed, more material will be removed. But after certain limit, the material removal rate will come down. Why, sir? It is the materials, the abrasive particles are increasing more in size. No, it has to remove more material. Okay, but how much gap is there? You see, there is a very little amount of gap. If you are having a very big material, then there won't be any material what you have other particles as well, which are very high in diameters. So what happens? Sometimes what happens? That particle may hit another particle, right? There is the big particle is hitting another particle, right? So it is losing its momentum, and then the loss in momentum is very high. That the momentum that is taken by the workpiece will be less. Okay, the moment that is reached to the workpiece will be less. So that's the reason why after certain increase of diameter of abrasive particle, the material removal rate come down. So it has some threshold value here, saturated value. Okay, so this can be asked in the HL examination. They might be showing some plots and they might be asking you to pick up the right plot. Okay, fine. This and all, let's not discuss much. Okay, let's discuss about abrasive jet machining. Okay, so what is abrasive jet machining? It is like ultrasonic machining only, but here there is no movement or there is no vibrations generated at in the tool. Here tool is nothing but nozzle. Nozzle is your tool. So what is happening? Let's see the schematic diagram. First, there is an air compressor. Why do you use air compressor? You want to compress air to a higher pressure, right? You're compressing it, and then that pressure. I mean, obviously, pressurized gas air will be flowing through some valve. Why you want to use valve? You want to control the pressure, and that air is passed to dryer. Why through dryer? Because if some kind of moisture is there in the air, that moisture will be removed in the dryer. So only dry air will be coming out. Moisture will be removed here. Now this dry air will be entering into filter because air might be having some particles, right? So there is some filter and filter will happen here, and then that pressurized air will enter into this chamber. And in this chamber, from the top side, you feed the abrasive particles. Now in this mixing chamber, what will happen? Your pressurized air and the abrasive particles will be mixing here. Now these abrasive particles with high pressure are entering in, are abrasive mixed with carrier gas will be entering into this nozzle. You know nozzle, right? It converts pressure energy to kinetic energy. You might have seen this in your thermodynamics, right? Nozzle, what does nozzle do? It will convert the pressure energy into kinetic energy, right? So this pressure energy is converted into kinetic energy at the tip of your nozzle. And that kinetic energy, who is getting kinetic energy? Abrasive particles are getting kinetic energy. In the sense, what is kinetic energy? Velocity. So abrasive particles are having good amount of velocity. Abrasive particles are having some mass into velocity, momentum. Here in this ultrasonic machining, momentum is created. Momentum of this abrasive particles are created because of the ultrasonic vibrations, right? But in this case, the momentum is created because of such kind of a mechanism. This is what is the mechanism. And the same thing, same mechanism. It will hit the workpiece, it will create some crack, then propagate, then brittle fracture. That is how this workpiece is being removed workpiece, I mean, material removal rate is happening in the case of abrasive jet machining. Is it clear, guys? How the material removal rate is moving in this AGM? Yes. Very good. Very good. What about others? Naveen is understanding. What about others? Okay. Okay. So this is how what are the advantages? Obviously, in this case also your workpiece need not be electrically conductive. So that's what they are saying. Any material which can be conductive, non-conductive, ductile, brittle, anything can be removed. Good dimensional accuracy is achieved. Good surface finish is achieved, and there is no need of coolant also. Why? You are passing air. Air itself is good enough for cooling the material. That to pressurized air. So fine. And disadvantages low MRR. And sometimes what happens if your material is ductile, if your workpiece material is ductile, sometimes these abrasive particles will be getting stuck into the workpiece. So that is a problem in the abrasive jet machine. So this is now let's go to this laser beam machine. Light amplification by simulated emission of radiation. This is what is called laser beam, right? So we might have seen in when we were kids, we used to buy some laser and we used to point it out at someone's hand, or maybe some point it out from long distances. Remember? So it has changed uh, the what you say, the some kind of different fields have been changed with the help of laser. It can be used as a sensor. It can be used in so many applications. We'll be using laser. Let's not go into deep about discussing how laser is generated. Let's assume that laser has been generated. That laser is having so much amount of energy. Now there is some kind of setup here. If you see, there's a flash lamp, laser crystal, reflectant, all these things you forget. The only thing is that somehow this laser is generated at this tip, at this end, and that laser is concentrated on this convex lens. As this laser is concentrated on this convex lens, what happens? The laser will be trying to focus onto the workpiece. The focus is increased, right? Here the diameter of laser is very high, but as the passing it through some lens, the diameter is getting reduced. So as the diameter is getting reduced, and huge amount of energy is being focused at some single point on the workpiece. Because of that huge amount of energy is focused on single point of workpiece, the workpiece is heated and then melted. And as it is getting melted, it will get vaporized. Okay. So the mechanism in which the laser is removing the workpiece material is by melting and vaporization of workpiece material. Okay. And this laser can be used for cutting the material and for welding the material, because heat is required for welding material. You can heat them and you can join them, or you can cut them as well. So this is what is called laser beam machining. Very easy. Simply you can pass laser through some lens, and then laser is concentrated on at some point where you want to cut or weld, and then because of high temperature, melting and vaporization is happening and cutting is happening. That is what is laser beam machining. Next. And obviously here you can, in laser beam machining, the important point is that as high amount of energy is concentrated at one point, the depth which is achieved, the depth of hole, let's say if you want to make holes, the depth at which the laser beam is achieving is very high, because high amount of energy at small amount of place, small amount of area, surface area. Huge amount of depth is achieved with minimal HAZ. What is with minimal HAZ? With minimal HAZ, it means minimal heat affected zone. So this is what is called heat affected zone. What is heat affected zone, sir? Okay, let's say if you take some block like this, you put some molten metal drop here. This is your molten metal drop. It means that workpiece is 100 degrees centigrade. Let's say this is some 100,000 degrees centigrade you're putting. So this metallic drop will try to get heat. I mean, some kind of metal is melted here, then some kind of material here will be heated and recooled, right? That heat which is affecting the workpiece, and it is creating some kind of a zone at which the heat is getting affected. I mean, the zone is getting affected with this heat. So the zone at which the workpiece is getting affected with the heat that has been put onto the top is known as heat affected zone. And because of heat affected zone, the material properties will be changing. The materials property of workpiece and the material properties of HSZ will not be same. Okay. So in this case of laser, heat affected zone will be very less. That is very important. And of course, again, workpiece need not be conductive. Obviously, it's good. Produce larger remelt zone, and you know, see that it can produce. See the diameter of hole 0.005 mm of diameter. Very small holes, deep holes, as I already mentioned. Right. So what is application? Application of that. But let's say if you want to make small holes in the blades of your jet engines, this kind of blade holes you can make into this blade, so that for cooling purposes, right? For cooling purposes, you want to make produce some micro holes. That micro holes will be made by using this laser beam machine. Okay. Next is nothing but electron beam. Again, please remember here, electron beam. Here also again, some some cathode grid is there, anode is there, some valve is there, everything you forget. And these are some kind of deflection and coils, where some magnetic coils is there, deflection coils are there. Somehow some electron beam is generated, and that electron beam is generated is trying to pass and hitting the workpiece with huge velocity. What is the velocity? 2 lakh kilometers per second. See the speed, how much fast it is traveling. 2 lakh kilometers in 1 second. That kind of speed this electron beam is achieved. And if you want to maintain this kind of a speed in an ambient space, it's not possible, because there are some other electrons which will obstruct the speed of this electron beam. So as to reduce that obstruction, what we will do, you'll perform this whole electron beam operation in vacuum, because the other elements should not obstruct the electron beam. It should have good as much speed as possible, as much velocity as possible. So that, please remember, electron beam machining is performed in vacuum. Okay, the whole setup, see, this full is kept in vacuum chamber. See, vacuum chamber. And when that electron beam is hitting the workpiece, same thing again, like laser beam, huge temperature, high velocity electrons are hitting onto the workpiece. Huge amount of temperature is generated, melting is happening, evaporation is happening. So again, melts and vaporizes. Okay, there it is laser beam, here it is electron beam. Laser, no problem, it's a simple light and all, some mechanism is there. But here electron beam is generated, and electron beam can be distracted by some other electrons in the ambience, and you don't want that to happen. So you're using all this, you're doing all these things in a vacuum environment, or you're doing in a vacuum chamber. Fine. Now let's see the diagrams in a summary. The summary is here. You see, this is what is your ultrasonic machining. Some abrasive particles are with some abrasive slurry, you can say, is in between tool and workpiece. Tool is getting vibrated, and momentum of abrasive particles are hitting the workpiece. The crack is initiated, crack is propagated, then it will fracture. ECM, again there is a gap here. NaCl, this is electrolysis NaCl plus water solution. And again here some chemical reaction is happening. Because of that, the workpiece and is being removed in the term of anodic dissolution. Why it's called anodic? Because workpiece is given positive terminal. Fine. See, positive terminal is given here. Next is abrasive particles are given with high pressure are allowed onto the workpiece with the help of nozzle, and because of that some metal is removed, and same mechanism is same, that is fractures is created, or maybe you can say crack is initiated, crack is propagated, then brittle fracture is happening. Then here medium, obviously like ECM we have some fluid, and that fluid is a dielectric fluid. For example, you can say kerosene is dielectric fluid in the case of normal EDM. In the case of bioidium, deionized water is the dielectric fluid, right? And there's a spark generated. That spark is momentary. For that momentary time, the huge amount of temperature with 1000 degrees centigrade is generated around. Because of that, workpiece will be melted and evaporated, right? So these are the important non-traditional machining process, and this is the summary for that. Okay, hope you're understanding it. And the last part of our machining is jigs and fixtures. So what is the difference between jig and fixture? So let me understand here. Jig is nothing but it holds, supports, locates. What is that, sir? It holds, support, locates. I didn't get, sir. Okay. Now let's say this is your drilling cutter. This is drilling, and this is your workpiece, and you want to make a hole here. I want to make a hole here. Okay, but now what I have to do? First, I have to make sure that this axis and this axis have to be in line, and you have to. Sir, I'll write a CNC program, sir. So then let's say it's not a CNC programming machine. It's a simple normal non-CNC program. This simple manual drilling machine. Then how would you make sure that it is exactly aligning with the this is what hole axis of hole, this is axis of hole, and this is axis of drill bit, Sir, how will you make this axis in line? Anyone? How will you make this axis in line? Otherwise, if your axis is little bit offset, then the hole will be offset, right? How do you make this? Anyone? If I want to make a hole here, this kind of a hole here, obviously my drill bit has to be having at this axis only, right? How do you make sure that this axis and this axis, or the point at which the drilling has to start, is exactly at this point? How do you know that? How do you make sure that? Anyone? Guys? Yes, with the help of jigs, obviously. What is jig here? It's a pre thing that you place in between workpiece and tool, in between workpiece and drill bit, and this is called carbon bushing. Now what you do? Already you reference this bushing with workpiece, and you had a reference where you can start this drill on the jig as well. So then that's the reason why they're saying it will hold the workpiece. Obviously it is holding on to the workpiece, it supports the workpiece, and it locates the workpiece. Of course, it is guiding the cutting tool. It is saying, hey tool, you go in this way. This is how this is the hole in which you have to go, so that you can make a proper hole on the workpiece. It is guiding the cutting tool. That is what is very important. Holding, supporting, all these things can be done by fixture also, but guiding the tool, guiding the cutting tool is very important, and that feature is available in jigs. One of the example is carbon bushing that I showed in the previous slide. So here these are holding, supporting, guiding. This can be jig. So locating workpiece can be done by jig, but it can't be done by fixture. So there's a difference between jig and fixture now. Let's discuss that. So what are jigs? Jigs are usually fitted with hardened steel bushings for guiding or other cutting tools. A jig is a tool of type of tool used to control location and motion control of another tool. Okay, fine. Where is fixture here? Okay, this is a bushing here. It means that this tool has to move in this direction in this space only. This is a bushing here, right? This is our boring jig actually. This is boring jig, and this is fixture. What is that? Fixture is same thing, but it doesn't guide the cutting tool. What is fixture? It holds, supports, and locates. Very important. What is that? Okay, let's say if you have this kind of a some kind of complicated structure workpiece, something like that. Okay, um, some kind of something like this. Okay, very something like this, and you have to make hole somewhere here in this. So what you want to do? You want to clamp it. You want to clamp it. Okay, like this, I have to make some 10,000 products. I want to make hole here, and these are 10,000 products. I want to every time make a hole here. So every time I can't clamp, right? I don't want to clamp it. Every time I remove, I clamp it. Every time I clamp it. So it's very difficult. Now what I do, I'll make some kind of fixture for that part alone. For some individual part, some fixture will be used. So no fixture is unique like part. So if this part is having some dimensions, of course, a corresponding fixture also will be having some dimensions. So what you do, you make some kind of a bed like this, where you automatically have some clamping system, and then you directly put the part here which you want to manufacture, and then obviously it will try to have some kind of a space where you can easily locate the workpiece. Of course, it will hold the workpiece, it will support the workpiece, it will locate the workpiece, and then you can keep on drill. You can keep on make the repeated operation again and again, and you can mass produce it. So the importance of fixture will come only in the terms of mass production. If you don't have any mass production objects, then the fixtures will not be justified there. Okay. The only difference between jig and fixture is nothing but the jig will guide the cutting tool. It's very important. Where we have seen the drill bit is being guided onto the workpiece. And fixture will not guide the cutting tool. That is what is very important. The difference between the jig and fixture. Is it clear, guys? The differences between the jig and fixtures? Yes or no? Okay. Okay. And that's the end of your machining. Okay. So let's do some problems. Let's do some problems. Before that, I'll give you some intro on metal forming. Okay. I will give you some intro on metal forming, and then we'll start some problem solving things, and then we'll end today's session. Okay. So let's go to that. So these are problems. Okay. Okay. Now let's start metal forming. Can you see the slide, guys? Can you see the slides? Okay. Very good. Very good, guys. Come on. Okay. Now, can anyone say what is the purpose of metal forming? Can anyone say in a very small lines? We have metal cutting, we have casting. Happily we can produce. Why to go for forming? So what is forming? First, what is forming? Anyone? Okay. You're shaping the material. You're shaping the workpiece into different. You're changing the geometry. You're not removing the material, right? In metal cutting, you're removing the material. It is a material removal process, right? In casting, it's kind of an additive manufacturing. You're adding the material, that's different, but you're having so many defects in that. In metal forming, you're not cutting, you're not removing the material, rather you're changing the shape of material. That is what is important. You're changing the shape of material to a desired shape by using some mechanical forces. That is what is a metal forming. Right? In metal forming, we have two categories. One is bulk metal forming, another is sheet metal forming. Based on the dimensions of the object, these two are categorized. Bulk, heavy metal forming, sheet, thick. So in sheet, the thicknesses are very less compared to the length. Okay, so let's proceed. Okay, so what is happening in these are the syllabus for metal forming. Anyways, in metal forming, generally if you are shaping it, in the sense you are applying some mechanical forces or you are applying some force. You are applying it compressive force or tensile force, be it something, but you are applying some force. Let's say if you are applying some tensile force on an object, you are just pulling it, you are pulling the object. What is happening if you are having a metallic rod of diameter D and length L or height H, let's say, then you are trying to pull. What will happen to the diameter? What will happen to the diameter if you are trying to pull? Guys, reduce. Length will increase. And once you remove the forces, what will happen? Once you remove the forces, what happens? You are pulling it, it will reduce. Once you remove the forces, will it come to the original place? Will it come if you are trying to apply? Okay. If you are applying some load like this, force like this, obviously it will be reduced and it will increase its length. Once I remove these forces, what happens to this object? Will it come back or will it not come back? Guys? Yes, in elastic deformation it will come. But in metal forming, do you want that? You're trying to apply some force and you want to change the shape. It is coming back. There is no point. Am I right? Are you getting my point? If at all you're applying some forces and your shape has changed, I mean your shape and all these things, these dimensions have changed. And immediately after removing the forces, if it is coming back to its original position or original geometry, there is no point in doing that. Why are you doing that? Simply you're doing it. You want the material to retain its shape. It has to not come back to its original position or original geometry. That's the reason why whatever we are discussing should be right side of this thing. This is the zone where we are working. This is your elastic zone. So that's the reason why after this zone only, it's called plastic zone. That is what is after yielding. This is called yielding point, right? Yield point. After yielding only, this plastic zone will come, and that is the zone in which we are performing this metal forming. Before this thing, so where do you want to use this elastic zone? Where do you want to use this elastic zone? Anyone? Where do you want to use this elastic zone? Okay, for forming I'm using plastic zone. I want my material to fail and it has to not come back. In which places or in which applications you want to use an elastic zone? You want to be in elastic zone? Anyone? In which place you want to be in elastic zone? In which applications or in which field or in which subject that you are at in your mechanical? Where do you do all the things in elastic zone? All the calculations in elastic zone? Anyone? Is it not strength of materials? You will read strength of materials and you want all the dimensions, you want all the calculations to be in elastic zone. Am I right or wrong? Yes, strength of material, machine design, all these things what you do. You don't want the material to fail, right? You design some things such a way that your material is not crossing the yielding. You don't want the yielding to happen in any case. Am I right or wrong? And also you'll try to find out when this yielding is happening and you will give some factor of safety and you will say that I will apply this much of stress only rather than using this much stress. So you'll use some theories of failures, right? You'll use some theories of failures and try to identify how it is failing, and then you'll use some factor of safety, and then you'll say, I want to be in a safer zone, so I'll give you so much certain amount of factor of safety. And then once you feel that the load is beyond that limit, then you say that it is going to fail, and I don't want to use that force at all. But here it is reverse. You want to go to a force where you want to change the shape, you want to, and also it should not come back. So it should be above the yielding point, and the region above the yielding point is after the yielding point is known as plastic zone. So we have to work in this zone. Good. And in metal forming, what happens in metal cutting? What happens? You have like this. This is your bar, and you want to cut this. You want to cut this. You want to make this kind of bar. So what you do? Let's say the grains what are there are like this. Initial grains are like this. So initial grains are, the grains will be cut. So what will happen? If you see this exaggerated view, the grains will be left like this. Full grains should be like this, but the grains were cut. But in forming, it won't happen like that because you're applying some force. No, you're applying some force. Instead of cutting, what will happen? The grains will be compressed like this. The geometry will be changed rather than cutting, right? So this is metal cutting. This is not good. This is good because the grains will be intact. There won't be any discontinuous grains. Okay, fine. And in metal forming, we have these things. This is called cold working. This is called warm working. This is hot working. What is cold working? If your temperature of working, if your working temperature is less than 40% of melting point. Let's say if the melting point is 700 degrees centigrade, let's say 500 degrees centigrade. What is 40% of 500? 40% of 500 is 200 degrees centigrade. If you are doing your metal forming at less than 200, let's say it is 100 degrees centigrade or 30 degrees centigrade, what is it? If you are doing your metal forming at less than 40% of your melting point, then it is called cold working. In between 40% to 60% of melting point, then this is warm working. And if you are doing your forming above 60% of melting point of material, then it is called hot working. Obviously, you are not melting it. You don't want to melt it. This 60% means this is some solid which is softer because of high temperature, right? So if you want your material become too soft, if you have very hard material, you want to form it, you want to change the shape of it, you have to apply lots and lots of forces. So instead of doing that, what you'll do, you'll heat the material. That is what you'll do, right? You heat the material becomes softer, then you change the shape, then you'll cool it, right? So this metal forming is there from ages, some decades, some centuries it is there. How did the civilization has grown? How this civilization has been developed? The ape man was there. All this old ape men, they used to forge these tools by using this metal forming only. How? In movies also you might have seen there are some kind of stone here, and you want to make knife. This kind of handle this knife, and you keep on it, and you heat it and hit it, and that's going to become a knife. And hero will take that knife and he'll do action sequences, right? Like that. So for forming is nothing but if hard material is there, you want to form it, you heat it, it becomes softer, and then you apply some kind of impact forces or some normal forces, and then you change the shape of the material, and then again you cool it, right? And what is recrystallization temperature? It's very important. What is recrystallization temperature? Recrystallization temperature is nothing but the temperature at which the crystal structure is one crystal structure is forming into another crystal structure. Okay, so when you're trying to, okay, I'll show you the diagram. There's a diagram. The diagram I'll show you. Yeah, this one. See here. So this is a rolling operation. You're trying to apply some force load here like this, and grain structures are formed like this. And as you keep on moving, the grain, these are like deformed, elongated grains, and it means that these are stressed. These are stressed grains. As you keep on moving, new grains are formed. You see, new grains are formed. some small grains are formed. And the conversion of this old stress grains to new grains, and these new grains are stress-free. Grains are stress-free. And this conversion of old grains to new grains occurs at some temperature. And that temperature is known as re-crystallization temperature. The crystals are changed. Re-crystallization temperature. Okay, so that is what is called re-crystallization temperature, and that re-crystallization temperature is approximately half the melting point of your material, of the melting point of a given material. Okay, next. Fine. Now let's discuss something on mean flow stress. What is mean flow stress? The stress at which the material is flowing in the sense plastically. The material should flow, right? So if you are trying to apply, if there is a block like this, you are trying to push, it is attached to the ground, and try to push, and the material has to flow in this direction, right? The material has to flow. How it is flowing? And that flow will occur at some stress, some force has to be applied. At which stress the material is flowing? Stress at which the material starts to flow, yielding, after yielding. So the material at which, this is all elastic zone, elastic, this is plastic. And the material at which the material starts to flow is this point. Hence, the mean flow stress is equal to yield stress in this case. Okay. In the second case, this is the point which the material starts to flow, and this is the region. All these things is a stress. So this is here UTS stress, and this is here yield. This is here sigma y, and this is here sigma UTS. So hence, what you do, the mean flow stress is average of these two values. Average of these two values. That is sigma y plus sigma UTS divided by 2. Okay. Next, if you have a very complicated curve like this, then this is given by this Holloman's equation. That is not Holloman's, like this is given by this mean flow formula. From Holloman's equation this will come. Okay, that is K epsilon T. What is epsilon T? Epsilon T is nothing but true strain. And guys, you should know the difference between true stress was engineering stress and true strain versus engineering strain. Do you know this? Yes or no? The differences between true and engineering. True stress, engineering stress, true strain, engineering strain. Do you know the differences between these two? Yes or no? Guys? Okay, Prakar doesn't know, Rishikesh doesn't know. Any other who knows about this? Okay, nobody knows. Okay, let me tell you. Let me come away from this flow stress. Let me discuss about true stress was true strain. Engineering stress was, sorry, true stress. Okay, let me go back. Let me start with some base. Okay, I'm coming again. If at all you have some object like this and you are applying some force. Right? Okay, you're applying some force like this, and it is having some cross-sectional area. Okay, let me draw like this. You're applying some force. This is your cross-sectional area, initial cross-sectional area, original cross-sectional area. Before applying force, initially it is like this. What is stress? What is stress formula? Anyone? What is stress? Guys? Internal resistance by area. That is F by A naught, isn't it? F by A naught. Am I right? You have to tell me yes. And it is elongating. It is elongated, but still you'll use after when it is elongating, obviously the whatever area that is there at some instant will be less than A naught. Am I right or wrong? As you are keeping previously, you only told if I am applying force, what will happen to my diameter? Diameter will reduce. As the diameter is reducing, at some instant, your area will be less than A naught. Your area will be less than A naught. Am I right? So this is your instantaneous area, right? So what I mean to say is that your instantaneous area will always be less than the original area. But generally what you do in stress, you write F by A naught. Directly you write this original area. You are not caring about instant area. So whenever you are writing this force divided by original area, then that is known as engineering stress. That is known as engineering stress. So by default, when you are seeing resistance divided by resistance offered resistant force or resistant force that is offered from the material divided by the original cross-sectional area is known as engineering stress. What is true? True is nothing but force divided by the instantaneous area. So as the load, the force is acting, the dimension of the area of cross section will be keep on decreasing. If you are trying to apply some tensile stress, if you are applying some tensile load, your area of cross section will be reducing. So instantaneous area will be keeping on reducing, right? So if you want to see the diagrams between true stress and let's say if you see this is your engineering strain and this is engineering stress. This is some kind of like this, you know, this is what is happening. It will come down fracture. But if you are seeing true, this is epsilon, this is true, then it will go like this and it will go up, it will go, it will not come down, Why? Because what happens, sigma T is equal to force by instantaneous, right? As this is happening, it is expanding like this. What is happening? Area is reducing. The area, as the denominator is reducing, stress will keep on increasing, right? The stress will keep on increasing. It won't come down. Okay. Now you understand the difference between the true and engineering. Yes or no? In true, what we'll do is that we'll divide the stress, the force by instantaneous area. In the engineering stress, what you'll do, you will divide the resisting force by original cross-section area. Are you getting my point? Clear or no? Yes. Very good. Now in this formula, this is what is the thing. Here it is not engineering strain. Engineering strain is what? Delta L by L. But true strain, this is engineering strain, but true strain sigma T will be change in length at that instant divided by the L. At that instant, how much is changing? That is important. This is total change in length. This is after full, how much after expanding, what is total changing length. But at an instant, some dl will be changed. At an instant only. This is what is true, dl by L. Instantaneous change in length by length. Total length will be giving a true strain. Please do remember that. So the formula of flow stress is given by K into strength coefficient into epsilon T to the power of n, that is strain hardening exponent, divided by n plus n. Okay. So this is how the flow stresses are calculated in these three cases. This is simply elastic, plastic, perfectly plastic. This is elastic, perfectly plastic. This is elastic, some plastic. Okay. Why it is called perfectly plastic? Because without any application of stress, it is increasing its strain. Ideal. It won't happen without applying any force. How your change in length will happen? It won't happen, right? So that's why it's elastic, perfectly plastic, and this is elastic, some plastic, and this is what is true flow curve. Okay, fine. And these are the formulas. These are the formulas for engineering stress, engineering strain. Engineering stress is P by original cross section area, load by original cross section area. Change in length, total change in length divided by the original length, initial length. In true stress, what is happening? Load divided by instantaneous area. At that instant, what is the area? And you can derive, and you can do some manipulations, and you can derive that true stress is nothing but engineering stress into engineering strain plus 1. Okay, you can derive that. I'm not doing the derivation, you can derive that. And true strain is given as from 0 to L, instantaneous change in length divided by length. And again, engineering strain is given as ln of natural logarithm of engineering strain plus 1. Okay, these are the formulas that you have to remember. Please do remember these formulas. This can be a question also in examination. And if your strength of materials subject, whenever your strength of materials is being taught, you'll be able to understand. Your strength of materials teacher will be able to explain this thing. Don't worry. I hope your strength of materials subject didn't start, so that you didn't go to that point. Once the strength of materials subject is started, then obviously your faculty will let you know all things. Don't worry about it. Again, it will kind of be a revision for you. Okay. Next, and this is what is called Holloman's equation, and this is the derivation of your flow stress. No need to worry about it, but you know this. You remember this flow stress for a normal material will be K epsilon to the power of n on what is epsilon? This is true stress, not engineering true. So K is strength coefficient. This is strain exponent. Strain hardening exponent. Okay, very important. So let me stop here for the introduction of your metal forming. Let's discuss about plastic deformation and yield criteria in tomorrow's class. And it's very important. And please, I recommend you to refer or revise some series of failures, especially your Tresca's criteria, and you revise your von Mises criteria in series of failures. Please revise this too, or at least watch some videos in online, or maybe you can read somewhere notes and come, so that I'll explain it to you in a very clear fashion. Once you read somewhere and come back, I'll be explaining you, then it will be very good for you. Okay, so please revise Tresca's criteria and von Mises criteria in series of failures, and attend tomorrow's class. It will be very useful for you. Okay, and we'll be using these two criteria for our metal forming, and then I'll tell you what is plane stress and what is plane strain. All these things are very important in metal forming. Okay guys, is it clear? Okay, so it's been like longer time we are discussing only concepts. Let's solve some problems on machining and metal cutting, and whatever problems we are solving today, that's enough for metal cutting. All the questions are there. I'll be posting in the WhatsApp group with key. Okay, all the questions which you are unable to solve in the class, what I'll do, I will provide the questions with key in the group. You can download them, you can answer yourself, and then check the answer key. Okay, so let's solve some problems. Okay, tell me this answer. Okay, let me select some questions. We've already solved all these things. There is no point in discussing again and again the same thing. Same thing again and again have been discussed here. Taylor's two life, everything is Taylor's two life only. So let's go and this. Okay. Okay. Tell me the 39th one. Tell me the answer of 39th one. The rest of the questions I'll be putting in the WhatsApp group with key. Please try to attempt them without seeing the key, then you check with the key. Any doubt, you can post the question in the WhatsApp group, we'll discuss. So for now, you just solve the question of 39th one. What is the correct sequence of following parameters in order of their maximum to minimum influence of cutting tool? Okay. So cutting tool, you are saying first two, depth of cut is having more effect on cut tool life. Is it what you are saying, Naveen? Depth of cut will have more than cutting speed, then feed. Is it true? What you are saying? Think again. Anyone? You are saying B. Okay. Okay. I go with Prakar and Rishikesh. But 3 is first. Why? Cutting speed is important because Vt power n is equal to constant. That is where we started. Obviously, velocity or cutting speed is important. Okay. Is it okay? And this feed rate can be thought of what? Uncut chip thickness, isn't it? Didn't I say this? Yes or no? Yes or no, guys? I told that feed is considered to be uncut chip thickness and depth of cut is what? Chip thickness. Yes or no? Yes. So now tell me, tool life is sensitive to uncut chip thickness or chip thickness? Now you tell me. The tool life is getting degraded very fast because of chip thickness or uncut chip thickness. What chip? Whether it is uncut or cut chip? What do you say? T1 or T2? So we already know this formula: V to the power n, F to the power of A, D to the power of B. Right? Hello. So what it is observed that this uncut chip thickness is having more weight, more influence on cutting tool life than the depth of cut. Okay. So feed rate is affecting more than the depth of cut. So answer is 3, 1, 2. So answer is D. 3, 1, 2. Clear? Is it okay? Next one. Next one. Somebody are saying D and somebody is saying C. Who is saying D? Praveen is saying it improves tool life and it reduces cutting force. It improves surface finish. Improves tool life is good. I know that. How it is important for cutting force? If I have sharp tool, if I am having blunt tool, not too much of blunt, obviously. Little bit of nose radius, will it have any effect on cutting forces? What do you say? I don't think so. It is having some effect on cutting forces, right? So this nose radius will strengthen the tool. Obviously, nose radius will strengthen the tool, not the workpiece. Obviously, it will strengthen the tool that is there. That's the reason why it increases tool life. Obviously, as it is strengthening the tool. And also obviously because of that increase in tool, I told already there are no some feed marks left. Because of that, surface finish also will be improved. True. But as I know that it has no effect in cutting forces. Okay, it has no effect on cutting forces. Okay, you are saying that it will increase in area of blunt edge. That doesn't affect much. Very small blunt edge. It's not a very high blunt edge. If you're increasing the blunt edge, then it will lead to vibrations. So it won't be much affecting. Okay, answer is 1 and 3 according to me. Yeah, it's negligible. You're right. Next one, 41. Come on. This is not aberration. This is attrition. There's no word like attrition. Okay, whatever it is like. Tell me the answer. Okay, I didn't say this, right? So, okay, I'll tell the answer. Okay. So, the question seems to be very odd. I don't know why it is not. Okay, I don't know. The options are not looking good. Attrition, abrasion, diffusion. Okay, let us keep this question aside. Let's discuss this a little later. Tell me this question. Tell me this question. 42nd one. What is this attrition? I have to correct this. Okay, anyways. Tell me the 42nd one. Built up edge. Why built up edge is coming, Rishikesh? You're telling about the previous one, huh? Tell me 42nd one. Okay. Any other answers? Anyone? Previous class I clearly mentioned. You want to even go revisit the recording in YouTube. There are 3 zones. Primary zone, which is in between. Okay, tell me primary zone is between what? Which two? There are 3 things here. What is that? Chip, tool, and workpiece. Primary zone is in between which two? Primary zone is between chip tool or tool chip, chip tool or tool workpiece or chip workpiece. Primary zone. Guys? Work to chip. You're right. This is a primary zone. Primary 1. Secondary. Secondary zone. Secondary zone in which one? Tool chip. You're right. This is secondary. And obviously tool workpiece is primary. And I told you already, in primary and secondary, chip is the one who will take maximum amount of heat. Then only tool comes. Right? And then workpiece comes. So obviously maximum here who is taking? Chip. So obviously answer will be A. Right? Answer will be A. Next one. Answer is A. Good one. Next one. Let me see if operation Taylor should experience this turn. And this you can do. This and all you can do. Okay. Tell me 44th one. Okay, tell me 43rd one. 43rd one to tell. We'll see how many can answer that. Tell me 43rd one. Because these kind of questions only will be asked. Tell me 43rd one. Come on. In a single point turning operation of steel with a cemented carbide tool, Taylor's tool life equation exponent is n is equal to what? He has given us 0.25. Good. If the cutting speed is halved, the tool life will increase. So they are saying that cutting speed is half, in the sense V2 is V1 by 2. That is what they are saying. Then they are asking what is happening to T2, whether it will increase. It will increase, but it increasing by how many times? That's very important. Rishikesh is saying 16 times. Any other answer? How did you get 16? You know the formula, that is V T power of n is equal to constant. You know that. Okay. Answer B for Prabhakar. Why 4? We have to see now. Okay. So we know that V1 T1 to the power of n is equal to V2 T to the power of n. We know that. And what is V1? V1 T1 to the power of n is like that only. And but V2 is what? V1 by 2 into T to the power of n, right? And this V gets cancelled, and I can say that T1 by T2, or I can write T2 by T1. It's good to write T2 by T1. Okay. Then I can write as T2 by T1, T2 by T1 to the power of n is equal to 2. Right? What is n? N is nothing but 0.25. 0.25. Can I write 0.25 as 1 by 4? Am I right? Can I write 0.2 as 1 by 4? Yes. If I write 0.2 as 1 by 4, then obviously what will happen? T2 is equal to 2 to the power of 4 into T1. What is 2 to 2 to the 2 into 2 4, 4 into 2 8, 8 into 2 16. How much is the answer? How much is the answer? Now tell me. Obviously it is D. Rishikesh has given right answer. Amazing. So this is how the questions will be asked. Okay, simple questions, but it is confusing sometimes if you are not making proper calculations, because we feel that like 2 to the power of 4 is 8. Sometimes you feel that you have to do that. 2 into 2 4, 4 into 2 8, 8 into 2 16. Okay, so answer is 16. So as I couldn't get proper answers from the previous question, tell me this answer, 44th one. Anyone? Fourth one. Yes, Rishikesh, you are right. Answer is 3, 1 by 3. Please do this question. It's 1 by 3. I'm not going to do that. You have to use the same thing. That is, what is that? 2 life test. Doubling the cutting speed reduces 2 life. So, doubling the cutting speed in the sense V2 is 2 into V1 and T2 is T1 by 8. Then he's asking what is the value of n. You can easily find it is 1 by 3. You do that. Okay. And then this crater and all we are slaying. And okay, tell me 46th one. 46th one. 46th one. Obviously, this in this tool you have this. What is this where? And what is this where? 1 and 2. What is one? Crater. And what is this? Flank. So obviously it is happening on the face of the cutting tool, and it is little away of crater, I know, but the flank I'm not sure. So answer can be B or D. Okay, let me check this. I'm not sure whether it is away or not. I'm sorry for that. Huh? Let me check that. But I think answer is, it should be away, but there's a possibility of answer of B. But let me check that. But it is on cutting edge only. Okay. That's planar and all you forget. Okay. This Asterix and all you forget and all. See. Okay, some questions. Tell me 63rd one. 63rd one. Come on. Obviously, I told you it has to be performed under vacuum. Why we are doing that? We don't want our momentum to reduce. What about next one? 64th one. 64th one. Obviously, it is because of ion displacement, right? ECM, there is no corrosion, there is no erosion, there is no fusion, only anodic dissolution, that is ion displacement. Okay, today only we have discussed. Okay, you answered the 65th one. In abrasive machining, if you're increasing the grain size, I already told you clearly this kind of question will be asked. Tell me this question. You should tell me. Clearly explained very beautifully. Come on, tell me this answer. Somebody are saying, everybody is saying D, and Guna is saying B. Guna, I told you, it increases and decreases. Clearly, I told you in the previous, today's lecture like this. This is D naught, this is MRR, right? It went like this, and some drop has happened. I told you what is the reason also. Answer is D. It increases and then decreases. Okay, answer is D. It increases and decreases. What about next one? 66th one. This I didn't say. Okay, tell me. Actually, what happens now? They are talking about the stock removal. Stock removal is nothing but which is already machined. Okay. So for stock removal, the electrolyte should, possess some kind of, resistance to form this passivating film. All these things are there. So, anyways, like in this case, the answer should be B. Okay. Um, because there is some layer that is formed and that layer has to be removed and all these things will happen. But anyways, the answer is B in this case. You have to remove this. Okay. Tell me answer of 67th one. What is the answer for 67th one? Again, it is D. There is no point in discussing this. 68th one. take one. Okay, I didn't say about this, no? Okay. So tool wear, obviously, when you're machining, when you're doing ECM, when you're doing EDM, when you're doing USM, all these things are having some tool wear as well. Tool also will be weared out. So the tool wear will be very less in ECM, then very less in EDM, then it will be in USM. So the tool wear will be very high in USM and very less in ESM. So now tell me the answer. Which one? ECM, sorry, not ESM, ECM less than, EDM less than. So obviously the tool wear will be less in electrochemical machining. You are right. What about next one? Sorry. What about next one? What about next one? Same thing. Okay. Next. Okay. Tell me 70th one. Last one. 70th. Somebody told B. Somebody told C. Last one. Okay. Now you have to understand this. In this, how the material removal rate is happening? Material removal rate is happening because of crack. First crack initiation, then crack propagation, okay, and then brittle fracture. Fine. What do you mean by toughness? What do you mean by toughness? What do you mean by toughness? Guys, what do you mean by toughness? Anyone? It is energy absorption capacity, right? If at all material is highly energy absorption capacity, so there is no point of crack at all. So answer is not higher toughness. If you are having high ductility, it means that it is having higher toughness. So this second also is not option. Yes. So if you have lower toughness, it means that it will lead to fracture immediately because the energy absorption is not good. As low toughness, crack is initiated fast, then propagated, then brittle fracture. So more removal rate will be happening in the case of lower toughness material. Is it okay? Is the concept clear in this case? Yes. The answer is C. Because energy absorption is there, but that abrasive fellow is coming and hitting the material, and for forming the fracture or for creating the crack, your toughness should be low. If it is having high toughness, then it is whatever you're hitting, it is taking. No crack. If there is no crack, how your material will be removed? It won't remove, right? So that is how you have to think. See, everything what I am teaching here, the concepts are interrelated. Some question is given in the sense there is a reason behind it. You have to think a lot. Simply you can't intuitively say, oh, this is right, this is wrong. Okay. So have you there's one nice book actually. I want you all guys I want you to read this book. It's not a technical book, it's not a mechanical book. The book name is Thinking Fast and Slow. Okay, let me show you in it's a very good book. It's a very good book by Daniel Kahneman. Not now, don't read now, okay? After your exam is done, you read. Yeah, this is the book. Okay, this is the book. It's very cheap. It's only 300 bucks, I mean 300 bucks or something like that. Okay. In this book, how you have to think, he'll tell you. Okay, when he's a Nobel laureate. So here, in this question, intuitively, what you'll feel is that good toughness. No, that's the reason why it can remove. That is intuitive. In our brain, the brain is split into two systems: system 1 and system 2. System 1 and system 2. System 2 is very intuitive. In the sense, it will say whatever it comes to brain. It won't think much. System 2 is a deep thinker. Okay, it will analyze, analytical. Okay, if I say 2 plus 2, immediately you will say the answer. That is system 1 giving the answer. If you say what is 200, what is 198 into 124, immediately you can't say. Some computation is going on. So system 2 has to come into picture. So this is what is there in that book. I am not going to get into details as well, but it's a very good book, and it will change the way you think. Okay, but don't read it now. You read it after your examination of your HL, whatever it is. Okay, so Thinking Fast and Slow by Daniel Kahneman. Read that. Okay. Anyways, like let me stop for today. I'll stop the recording and